Hello everyone, welcome to this video. Today we're gonna cover layout strategies, and this is part of the industrial engineering program. So, strategic importance of layout decisions. So, the objective of layout strategy is to develop an effective and efficient layout that will meet the firm's competitive requirements. And so, layout design considerations are volatile, they change, so they are higher utilization of space, equipment, and people. And also, we need to make sure we have improved flow of information, materials, or people, and improved employee morale and safer working conditions. And also, customer and client interaction. We need to make sure we have that interaction and also flexibility. So that's the layout design consideration, things we need to consider. We need to consider the utilization of space, equipment, and people to also minimize the waste or wait time that's wasted during our production. And also we need to have improved flow of information, materials, and people. We need also to have improved employee morale and safer working conditions. And there are different types of layouts. So first we have the office layout, okay, which is a regular office that you found in any building. That's the office layout. And then there is the retail layout, okay, so which allocates display space and responds to customer behavior. Okay, so that's a retail layout, which is the retail stores basically. And so there is also the warehouse layout, which is basically the warehouses that we have. And also the fixed position layout, which addresses the layout requirements of large bulky projects such as ships and buildings. So this is fixed position layout. And then the process oriented layout, okay, it deals with low volume, high variety production. Okay, so this is process oriented layout. And okay, so this so process layout, so also called job shops. So process oriented layouts are also called job shops or intermittent production. So this is an example of this is operation rooms, so ORs, and also hospitals. So they are job shops called job shops. They are low volume but high customization or high variety. And so so there's also the work cell layout, which arranges machinery and equipment to focus on production of a single product or a group of related products. Okay, so arranges machinery and equipment to focus on production of so to produce a single product of or a group of related products. So this could be more of the product focus, so work cell layout. And then there is the product oriented layout, which seeks the best personnel and machine utilization in the repetitive or continuous production, so better for repetitive production. And so we have the layout strategies. So first we have the office, which locate workers requiring frequent contact close to one another. And as you can see, that's basically the layout strategies here summarized. So retail, warehouse, project, job shop, work cell, and repetitive continuous product oriented layout. So we have around 7 layouts here that we can deal with. Okay, and so some good layout considerations. So should consider the material handling, the equipment that will handle the material, its place and position, and also it's going to consider the capacity and space requirement of that layout. Okay, so how many people are going to be there, the space, and etc., and also the environment and statistics. Okay, so like the environment, the total the environment and the place. And so also the flow of information, so how is the information spreading between labor and people. And so there is also the cost of moving between various work areas, so that's another cost. So you need to move between different work areas, and that's a cost. And so you need to consider that because it's an important thing, and we're gonna now show you how we're gonna deal with that. So this is a process oriented layout. So this is based on the process, and basically similar machines and equipment are grouped together. So in the process oriented layout, the machines are grouped together, okay, and also in the process oriented layout, they are flexible and capable of handling a wide variety of products or services. Okay, and also scheduling can be difficult, and material handling and labor cost can be high. Okay, so it has high material handling and labor costs, and it can be difficult to set up. So there's surgery, ER, triage room, emergency room, admissions, laboratories. This is an example of a hospital. Okay, and it's important, the distance between different rooms and different, departments, because there are some considerations. For example, for blood and stuff like that, you don't want that to be near the ER or emergency room, the OR, operation room. Maybe you don't want to the blood and stuff like that, hygiene for purposes like this. So it's important to have just some distance between them. And so this is also a process-oriented layout. So this is the same. No, this is a different. Actually, this is a factory manufacturer. Yeah. So there's the grinding department, receiving and shipping, assembly. As you can see, the lathe department, mining department. So these are all studied. So it's not like put randomly. So I'm gonna put like the mining department near the grinding department because I wanted it this way. So it's not that way. It's calculated, and also the drilling department. So maybe I will need some, and the painting department. So I will need. Yeah, so it's based on the process also. So after the drilling is done, we take it to the painting department, as you can see, and then after the painting department is gonna go to the assembly, and then through the assembly is gonna go to the receiving and shipping, and etc. is gonna go to the lathe department, and the mining department, and so on. And that's why it's process based, and also takes into consideration that transportation cost and time. So it's important. And so there is the process-oriented layout. Okay, so to arrange work centers so as to minimize the cost of material handling. So minimizing costs, and basically basic cost elements are number of loads or people moving between centers, and distance loads or people move between centers. So we want to minimize cost, and this is the equation to minimize the cost. So I equals 1, j equals 1, and xij, cij. Now we're going to see exactly, visualize how this is done. And so basically, so n is the total number of centers, ij individuals, xc number of loads. And so the process layout example, let's see here. So we want to, for example, we want to arrange 6 departments. Okay, so we have a factory, and we want to arrange 6 departments to minimize the material handling cost. So each department is 20 by 20 feet, and the building is 60 feet long and 40 feet wide. So we have a 60 feet long, 40 feet wide building, and we want each department to be 20 by 20, and we want to do that in order to minimize the material handling costs. And so the first step that we need to do is we're going to construct a from-to matrix. Okay, so we're going to, make sure, you make sure the distances. So we have some criteria for the distances, so where we want it from and to where we want it to go, and then we want to determine the space requirements and develop an initial schematic diagram. So we want to determine how much space do we want and need, and then develop an initial schematic diagram, and also determine the cost of this layout. Try to improve the layout, prepare a detailed plan. So these are the steps that we're gonna do in our example. So let's see, this is our table that we're gonna develop. Okay, so process layout example. Now, number of loads per week. There is assembly, painting, machine shops. These are all the departments, the 6 departments. So we have this, what we call it, the matrix, the relationship matrix. Okay, so yeah, so to relate to the different departments. So painting, machine shop, receiving, shipping, these things. So number of loads per week, department, and etc. So yeah, so the number of loads are gonna be, for painting and receiving, there is a load of 50 for transportation. As for assembly and machine shop, there's a load of 100. As for machine shop and testing, load of 100, etc. And so there is the process layout example. Okay, so the process layout example has area B, area A, area B, area C. Okay, and so this is our 60 by 40 room, and we have also area 1, which is assembly department, area B, painting department, area C, machine shop department. We have receiving department, shipping department, testing department. These are all testing departments in our little factory. This is not a little factory, that's 60 by 40, okay. Okay, and then we do have, this is our matrix, so process layout example, let's see. So basically we drew this diagram, so we have assembly, painting, machine shop, receiving, shipping, testing, all of these. So as you can see, inter-department flow graph, this is the flow graph, and basically it requires 100 material, whatever that material is, maybe, let's say, oil, gas, like material for transportation. And so we're gonna have 100 from assembly to machine shop and testing. So this might not be the optimal. So, and how can we find the optimal? So there are several, programs and tests that we can run in order to optimize this. But maybe one example, if we change testing and painting, maybe we change them, we can get a better result for us. So we're gonna minimize this 20 and also minimize this 100. Maybe we can do that. Can change those, and also, yeah, so we can change that. Can maybe change this and just, so there are different ways, and it's hard to see it here because also the dimensions are not representative of the real numbers here. And so yeah, so we can go through some calculations, as you can see. So process layout example, so the cost is going to be basically $50 from 1 and 2. So where is 1? This is 1. Up to 2 is $50, and it's going to be $200 from 1 to 3. Okay, and so why is it $200? Well, basically, is it because we're going to go 2 units? Okay, so it's going to multiply by 2. I think that's the reason. And then here 40 from 1 to 6. Now it's 2. So assumes that the forklift is okay, so yeah, so moving a load between non-adjacent departments will cost $2. However, if we move load between adjacent departments, it's gonna cost $1. So that's why here we have 200, because assembly and machine shop are not adjacent, and the same for assembly and testing job. So this is the reflective of real life, kind of reflective of real life, that if you wanna to change to non-adjacent departments, you're gonna see that you're gonna see that we require more material. So yeah, and so here 2 and 3, between 2 and 3 we have 10. Okay, 2 and 3. Okay, so we have 30, yes. And then between 2 and 4 we're gonna have 2 and 4 we're gonna have 10. Okay, so I think there's a mistake here. Should be 50 according to this. Oh, 2 and 5. 2 and 5. Okay, so 2 and 4 is 50, 2 and 5 is 10, they are all adjacent. Now 3 and 4, they are not adjacent, so we're gonna multiply 20 here by 2. And also for 3 and 6, we do have 100, they are adjacent, so we're gonna multiply it by 2. And then we do have 4 and 5, so 4 and 5, and it's $50, and yeah. Okay, so this is our revised interdepartmental flow graph. This is our cost, and we can maybe model this and try to minimize this. There are different ways we can do this. So computer software now. Graphical approach only works for small problems. Okay, so yeah, this is a basic problem that we can, draw a graph for it and try to find the minimum, like a little puzzle. But the thing is that we have more complicated, bigger problems. We need to get the aid of computer programs such as Craft, ALDEP, ALDEP, okay, Factory Flow, ProPlanner, and CoreLab. And so ProPlanner flow path calculator generates material flow diagrams, calculate material handling distances times cost, and color-coded flow lines. It helps identify excessive material handling. And so we have, so computer software. There is also some visualization software that allows managers to view possible layouts, and that's very cost effective, since you don't need to go actually and build the thing and then you think that no, maybe I can do something else, and it's built by Siemens. So it's interesting. handling efficiency and safety issues. So there is also the work cells. So yeah, so we talked about the work cells. So there's an arrangement of machines and personnel that focus on making a single product or family of related products, and group technology identify products that have similar characteristics for particular cells. So there are the car door assembly work cell, frame and panel installation, windows and mechanism installation, electrical wiring, power windows controls, door locks and speaker wiring. So, and we have the handle and lock fitting, interior panel installation and quality check and testing. So car door assembly work cell, okay. So, and there are some advantages of work cells. So of course the advantages of work cells include reduced work in progress inventory, less floor space required, reduced raw material, reduced direct labor cost, heightened sense of employee participation, increased equipment and machinery utilization, reduced investment in machinery and equipment. So these are the advantages of work cells. Now let's see the Z layout. So we can improve layouts using work cells. So as you can see, we have this current layout workers in small closed areas. Okay, so there is the material. Also improve layout, there is the cross-trained workers that can assist each other. And as you can see here, basically the co-workers can assist each other in this. And also we can add a third worker as an additional output if needed. However, here it's hard to add another worker, just 1 and 2, and here is just if we have more load we can add another worker, which is an interesting thing. Now there is the current layout, which is straight lines, which make it harder to balance tasks because work may not be divided evenly. And there is the improved layout in U-shape. Workers will have better access and for cross-trained workers. The workers can be reduced to 3 basically, since if they finish something here, you can go back to there, and it's more, it's better in the assembly for us. And here, so here is just a layout straight lines, as you can see, and there we have, So now we have the product-oriented layouts. So it has advantages. Some of these advantages include low variable cost per unit, low material handling cost, reduce work in progress. So this is more like mass or product focus. Okay, so product focus is more product oriented layouts, and then easier training and supervision. We said we don't need very skilled labor for product oriented layouts, and then run it through bot. But there are some disadvantages, which include high volume, okay, and work stoppage at any point ties up the whole operation, and there's also lack of flexibility in product or production rates. And we have assembly line balancing. So basically this assembly line balancing its objective is to minimize imbalance between machines or personnel while meeting the required output. So this is like optimizing or minimizing the imbalance between machines, and it's like reducing the wait time and the wasted materials, let's say, or time. And it starts with the precedence relationships, and it determines cycle time, and also to calculate theoretical minimum number of workstations, and balance the line by assigning specific tasks to workstations. And so as you can see here, this is the wing component example. So we have 480 available minutes and 40 units. And so, okay, so there's some graphs. So assembly time in minutes, as you can see, task must flow. Okay, as you can see, so the task must flow. So the precedence relationships. So as you can see, this is the precedence relationship, and then so as you can see, it goes from 1 to B to D and C and F, and then 7, G. So we have the cycle time. So production time available per day over the units required per day. This is the cycle time. So so the time per the units per day, and we have also for our examples 12 minutes per unit. That's the cycle time. And the minimum number of workstations is the sum of time for task I over the cycle time. So if the total time for our product is 65 minutes, and the cycle time is just 12, so it's gonna be just 5.42 or 6 stations. Okay, so we'll need 5.42, but we cannot have point stations, so we're gonna round up, which is gonna lead us to 6 stations. Now Yeah, as you can see. Yeah. So layout heuristics that may be used to assign tasks to workstations in a simple line balancing. So longest task time. From the available tasks, choose the task with the longest time. You can see the longest time. Most following tasks. From the available tasks, choose the task with the largest number of following tasks. Okay, so rank, positional weight, shortest task time, least number of following tasks. Okay. Okay. This is our one component example. Now we change the stuff. So for here it takes 10 minutes, 11 minutes. Now the sum of these is just sum of the station 4. So we're dividing the stations. So 5, 4, and 3 is the sum of it is just 12. And then we have here 11 minutes, 11 minutes. So, and here we have 11 minutes. And so we have 6 stations. Now we're going to have some, added time here 12. So the cycle time is going to be 12 since we cannot have fractions. So we need that cycle time. It's inevitable. And so this is the win component example, as you can see. Okay, and so the efficiency is basically the sum of task times over the actual number of workstations times the largest cycle time. Okay, so here we have the sum of the cycle times for all the tasks is 65, which is divided by the actual number of workstations, which is 6. Have 6 workstations multiplied by 12, which is the maximum cycle time or the largest cycle time, which is 12. And so we have efficiency of 90.3%. But there is an idle time, which is basically 6 stations times 12 minus 65 minutes times 7 minutes. So minus 65 minutes. 16 stations times 12 minus 65 minutes. So there's an idle time of 7 minutes in our overall production line. And that's it. Thank you for watching. I hope you benefited and this video was helpful to you. Thank you very much.